a lot of people will be out of it. No, this is not what I want. I want teams.
Yeah, we have a whole team and not an excuse to play Mario Kart.
Yeah,
Our whole team. Molly, what's Molly leaving? She's leaving tomorrow, but I think she's gonna be there. She better. How about now? How are people missing our final grade equation? So,
Oh, is that today?
Yeah.
Oh, I didn't finish that or even start it.
well, that's next period.
I can multitasking math.
Yes, 400.
Okay. Guess it's just us today. We'll see if more people show up. Maybe they had a crazy. I had a crazy morning too. I had to run the Safeway because I think one of the tournaments is going to end today. For 6th period, my math Rio part will end today, so I have to go get a bunch of shit.
Still that got disqualified.
No, they just didn't have as many teams.
Qualified 2 days ago.
Oh, I forgot your 6th period. Sorry, I didn't mean to you. Trash my 6th
And I
period.
cheated. And I cheated, and that's why I got disqualified.
But they're not. There were 2 teams.
But did the other team get disqualified as well?
Yeah, I thought about it. They were like, they didn't mean to cheat, neither did Kian. But it's like right in the rule, even if you didn't mean to. So yeah, I just called. Anyway, all that is in the video. Now let us learn. Okay, so last thing I taught you was about these Taylor and Maclaurin polynomials, where really the idea is if you have some sort of weird, like sine of x is weird function. Like I said, it's like just a list of triangle ratios. It's not some algebraic thing that you get from taking square roots and stuff like that. So when you have functions like that, it might be a good idea, or it might be easier for your computer, or it might be easier for you to approximate this using a polynomial. And so the way we do it is we match the function value, the first derivative, the second derivative, the third derivative, fourth, etc., up to a certain amount. And the more terms you go, the closer the polynomial will get to the sine function. Actually, this one is kind of fun to see. Remind me if we have time later, we'll do this on decimals because it's fun to see the polynomial start matching the way. Yes.
Just a very quick question. In general, do the sine converge?
Yeah. E to the x, sine of x, cosine of x. And those are the big 3 that are very, very commonly used, and they converge everywhere. Like if you go enough terms, if you go infinite number of terms, they'll match the whole graph. Kind of neat. But actually, that's a good lead up as to what we're learning today. But first, we left one blank from 10.6. And this one, they tend to, I've seen this on the AP tests, like the full-on actual AP test, not the practice test, but real ones from previous years. They like asking about this Lagrange error bound, or at least they asked about it really, really recently, like a year ago or 2 years ago on one of the FRQs. And basically what it says, well, here's what it says formally. Like that's what you'd see on the textbook. But what it says in practice is that if you, like I said, if you approximate using 5 terms or whatever, then this tells you how far off you'll be from the actual function, like how far off your approximation will be from the actual value of the function. And let me get into the like very, very intricate details of this later. But basically what it says, remember the alternating series test or the alternating series bound that said, if you stop at 4 terms, the error will be the 5th term. This one in my brain, just to help me remember it, I think the exact same thing. Look at, if I stop at n terms, then the error will be basically the next term. Stop at n terms, the error will be at most the next term. If I stop at 5, the error will basically be 6th term. Basically, there's a little bit to it that's weird, but let me get into that later because in my brain, that's what I store so that I don't forget it, or so that it's easy to remember. Okay. All right. So here's the here's one example. Your homework has more that are a little bit different than this, so maybe one day we should go through that together. But for now, let's do this one. It says the function f has derivatives of all orders. Assume that f of 2 is 6, f prime of 2, f double prime, f triple prime. Gives you a bunch of stuff. Then it says write a third degree Taylor polynomial about about x equals 2, and use it to approximate 2.3. Okay. The third degree Taylor polynomial is what we learned last time. Remember, it's like we say, well, the way we've been writing it is third degree polynomial of x is equal to, and then here's like 15 seconds for you to try to remember how these go. Yeah, I don't know if that was 15 seconds, but remember the way they go is you basically write a polynomial where each term is the coefficient of each term is a different derivative of the function. So you start with the constant term being the 0th derivative, and then the function value itself, plus first derivative times x. Normally, except this is around 2, so times x minus 2. And technically that's to the first power over 1 factorial to deal with all the derivatives that you're taking, remember? And then minus 7 for the second derivative times x minus 2 squared over 2 factorial. And then plus 8 times x minus 2 cubed over 3 factorial. Remember, motivation for this is like x minus 2 to center it at 2 to shift the function over by 2. Squared so that the derivative matches the second derivative matches the second derivative here, and over 2 factorial because each time you take a derivative, you're bringing down a new power multiplying by it, and you want to like cancel that out. Is this ringing a bell? Okay, cool. Factorial. The factorial means 3 times 2 times 1 because each time I take a derivative, I'm going to be multiplying by 3, then by 2, then by 1. So I want to divide by 3, 2, and 1. Nice. Cool. Okay, so there's the third degree Taylor polynomial, and it says use it to approximate f of 2.3. You guys can probably guess what I'm about to do. What is it? It's this dude exactly. Yeah, exactly. The tangent line approximation is one of these. Look at it's exactly one of those, but just first degree. Now we're being fancier and doing third degree polynomial. So anyway, here's me plugging in 2.3. So say 4 times 2.3 minus 2 minus 7 times 2.3 minus 2 squared over 2 factorial plus 8. Okay, and then if you took the time to calculate that, you would get you would get 6.921. Meaning f of 2.3 is about this much.
Definitely.
What?
For the, could F 2.3 equals.
Oh,
Oh, we have to do the error
correct. Nice. Yeah, that's what's coming up. All right, it says the fourth derivative of f satisfies the inequality that it's always smaller than, or at most 9 for every x in the closed interval from 2 to 2.3. Use this information to find a bound for the error approximation of f of 2.3 is blah, 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 blah. Okay, so error approximation. Oh, shoot, I'm going to need more room. Error approximation, this is the thing that I was just talking about just now. Right, so let me make this small. Give myself more room. Okay. So part B, like I said, the only thing I told you so far is that if I stop at 3 terms, my error will be the 4th term. So that is the case, except it's the 4th term kind of altered a little bit. So watch this. The error for the function will be at most, now it's not like the alternating series bound where we're jumping back and forth and the next jump will be the biggest jump that you'll take for the rest of the time. So it's not exactly the 4th term. It's like the biggest that the 4th term could get, which is why up there it tells us the biggest derivative, or the biggest that the 4th derivative could be is 9. And if they don't tell you what the biggest they could be is, then you kind of have to figure out what the biggest the 4th degree could be is. But that's not that hard to do because, well, we'll talk about that when we get there. But okay, let me get this one done. Like I said, if I were to put a 4th term here, that would be kind of the error. Okay, the 4th term of this would be 4th derivative times x minus 2 to the 4th over 4 factorial. So that's the kind of little template that I'm going to put here. And then, like I just said, it's really not the 4th term exactly, but the biggest that the 4th term could get. It tells me the 4th derivative can be as big as 9. So the biggest it can get is 9 right here. And the biggest this could get is if I plug in, the biggest this could get in the interval from 2 to 2.3. So like from your center to the point you estimated, the biggest this could get would be if I plugged in a 2.3. I hope you agree. Like I just got to make this as big as possible. Okay, biggest I can get is 2.3. Okay, so my error will be I kind of here's me saving my notation because I'm about to put 2.3 into that. And I didn't want to say something with x equals something with just numbers. They hate that on the AP test. So now I've said, okay, I'm going to plug in 2.3. And so then the biggest this could get is 9 times 2.3 minus 2 to the 4th over 4 factorial, which looks a lot like the 4th term. Like that's why I just stored it in my brain and the error is the 4th term. All right, and anyway, if you calculate this, you get 0.0030. I just put the 0 here because I always go 4 term. I guess we'll just a 0.003. Cool. So now we've just said the error is at most 0.03. That's the answer to the question. You got one key in the question.
Yeah, I'm just kind of confused as to why it's just like why is it just a 4th term or whatever, like 4th just you only need one more term because like that's just reminding me of alternating series.
Yes.
Where you only need one, but this one is not necessarily an alternating series.
For sure, it's not an alternating. Oh, well, you're right. Not necessarily alternating. Well, I mean, for sure, not alternating. But correct. You don't need. That's what I keep saying. I store it in my brain as just the next term, just so I don't have to remember all these little details. But it's not. This would not actually be necessarily the 4th term. It would be the biggest I could make this 4th term.
But then what if you just had a 5th term that's positive, and then you still have the biggest 4th term? Like what do you?
You don't. That it has to do with some fancier math.
I guess I'm just confused on what the max is, like where the max number is coming from. Where you do or it's like like in this one where it says that on B, like F4 of X is less than or equal to 9.
Yeah.
Like where is that number coming from?
Oh, that number they gave us in the problem. But in general, you just kind of like if you had the 4th derivative. Like I think one of them on your homework, I don't remember them exactly because I haven't done your homework in a year. But like I think one of them on your homework is something like this. And so you look at this and you're like, the biggest that this derivative could get would be if I plug in the biggest number. So like let's pretend we're dealing with the same center and same number that I approximated. So I'm looking at this interval still. the biggest I could make this, well, this is an increasing function. The bigger number I plug in, the bigger the function gets. So that would come, if you were finding the max yourself, that would come from you plugging in 2.3.
So is the max just like the Y value you get?
The biggest phi value that you could get.
Okay.
And then why does that approximate the whole thing? Why don't I need to worry about the fifth, sixth, seventh, eighth term? That has to do with a little bit of fancier math than I'm willing to get into right now with 20 minutes left. But it has to do with kind of the mean value theorem and kind of this remainder theorem. Like, if you do long division, I don't know if I want to get into it, but if you do long division on any function, you're going to get some quotient and some remainder. And it's that idea where it's like, okay, if this is my first three terms, then my remainder will be I just underlined the wrong thing. But basically function plus remainder equals the whole quotient of long division. And again, this also has to do with the mean value theorem generalized to more than a single derivative, but like many derivatives. But like I said, if I tried to remember the whole proof of it, it will take me longer than 23 minutes. Because to be honest, I don't remember the entire proof. But the idea is that at some point, the function value equals exactly some number plugged into the fourth term. Yeah, okay. So mean value theorem says something like that about the first derivative. You can generalize that to any derivative. That tells you the actual function value at 2.3 or whatever is equal to some number plugged into the fourth term.
So you can get the max from it.
Exactly. Yeah, then the biggest the error could get is the biggest that the fourth term could get. Yeah. Nice. Okay, part C. Could f of okay, we're almost done with this. These are all just kind of basic questions. It says, could f of 3 be equal to like the actual value? Could that be 6.922 based on our approximation of 6.921? And do you guys know how you would figure that out? Oh, I see. Yeah.
Over CP error.
Yeah. Okay. Yeah. Okay. You guys are thinking of it backwards than me. I thought of here's our approximation. Here's the biggest the error could be. So let me add those, which is what Kian said. You could add those. Or you guys are saying how far is this from what they're interested in, and is that bigger or smaller than the error? Either one is doing the same thing. I guess I'll do it. Since I already had the answer ready my way, let me write it like that, because that way I can succinctly write it. So f of 3 could at most be my approximation plus how far off I was from the actual value, or like the maximum that I could be off, but from the actual value. So plus 0.003, which of course, if you add that, that's 6.924. So yes, could it be 9.22? Well, we said that the actual value has to be less than 6.924. This is less than that. So yes, it's plausible that it could be within the error. So running out of room. So let me just say this implies that yes, it could be, because it's within the error. But D, could it be in 6.927? No, according to the calculation I just did, it has to be under 6.924. 27 is bigger, so I'm going to say no. F of 2.3 has to be less than or equal to 6.924 by Lagrange error bound. Lagrange error bound is what we just did. This error that in green that we discussed. Nice. Or you could say this is outside of the bounds of the error or something like that. I don't think you have to
Good morning.
mention Lagrange error bound. Hello.
I am the sub in this class.
Oh, for Healy? Nice, okay. This is actually a different class. Like, we don't start our class doesn't start till 8:50. But you're welcome to hang out here.
Oh.
Okay, so questions on the Lagrange error bound? Okay, when you get to the homework, you might run into questions, but that's what I got for this one. Not super hard because they told you what the biggest thing could be. Once you get to your homework, I think you have to figure out what the biggest this could be and what the biggest this could be, and basically plug in the biggest number into those.
It's just that you just plug in.
Yeah, it's usually just plug in either the biggest number, if it's like an increasing function, or if it's like 1/x, which is a decreasing function, then plug in the smallest number, in which case I would have plugged in 2, like that would be the smallest as possible. All right, next one though, we have like 20 minutes to learn radius and interval of convergence, which we'll see if we get through, but if we don't, that's fine, because we can do it tomorrow. But okay, this page, I don't think it tells you anything new. So I'm not going to read it word by word, but basically they're saying, all right, these power series that we just saw, like x minus 5 to the third over 3 factorial, that if you consider that a whole function, then that's what people call a power series. So the power series are exactly what we were just doing. X minus center to the power of over that thing factorial. That's a power series centered at C. If you consider that a whole function, then that's cool, except that you have a chance of, what if you're trying to figure out what is f of 7, and f of 7, you plug in 7, and now this series does not converge. So you catch what I'm saying? You have this whole sum. Sums, we know sometimes they converge, sometimes they diverge. Okay, now you're putting x's into that sum, as in if you plug in 3, you have this sum 3 minus c. Okay, but are there numbers, or for sure there will be numbers that that if you plug them in for x and you evaluate that sum, now it does not converge. So the idea, let me make this look nicer by giving myself some room. Okay, so the idea that we're learning in this section is what x's can I plug into here so that the resulting sum converges or diverges. Yeah, it's basically usually just, no, well, it's always like you can plug in numbers between 0 and 1, or like this is an example. Plug in numbers between 0 and 1 and it'll converge, plug in numbers bigger than that and it'll diverge. So this looks very abstract, so let me give you a quick little easy example. Okay, that would be like an easy little example to get you like to understand this. So here this looks like a geometric series. Yes. Okay, cool. We know the geometric series converges if what's true. Nice. Yeah, if this dude right here is less than 1. Okay, meaning that if I consider this a function, then I could plug in 0 would work, then I get zeros. I could plug in 1, I could plug in 2, I could plug in 2.9. But as soon as I plug in 4 into this, then this sum diverges, and so the function doesn't make sense. You know what I'm saying? So this function would have an interval of convergence between whatever numbers I just said, 0 and 3 or whatever. Or actually negatives would also work, because then that would make it alternating, but we'll get there when we get there. Okay, so that's the idea, is what can I plug in here? Point by point, I plug in a 1, now this is a totally good sum. This is how I think of it. It's like plug in an x, then evaluate the sum. Plug in, it's like pointwise. You're plugging in an x. Oh, look at the sum. Does it converge? Plug in another x. Does it converge? This is what picture shows up in my brain. Because there's so many variables in here that it's like hard to keep up with it. I think of, oh, this x is kind of a constant once you plug it in. So that helped me like conceptualize it. All right, anyway, that's what's going on. So how do you figure out what x's you can plug in quickly without like just thinking about it? Well, 2 sections ago, we learned this really helpful thing called the, actually, I'm skipping ahead a little bit, but we're gonna be talking about the ratio test in a second. I just forgot that there could be 3 possibilities. Like this dude right here that I just gave you has an interval of convergence of like -3 to 3 or something like that. If we thought about it harder, I could tell you specifically, but this dude right here, -3 to 3, so that would be case number 2, where between 2 numbers, you can plug in any number into that x, and it'll converge. Another case is it never converges, like this sum is always too big. The only time it converges is if x is 0, like if I get a sum of 0 plus 0 plus 0 plus 0, okay, that converges, but nothing else does. That's case number 1. And then case number 3 is like this shrinks small enough that it does not matter what I plug in for x and it converges for all real numbers. And that's the case for like Anand was saying. That's the case for e to the x, sine of x, cosine of x. Those always converge no matter what x's you plug into their power series. Cool. All right. And then that would be intervals of convergence. Radius of convergence is basically from the center to the end point of your interval. Like what's that distance? But we'll get there. When we get there, let's get to an example. Like I said down here, I think it talks about if you're asked to find the interval of convergence, you have to do the ratio test. And it says something important here in bold. But before you guys fall asleep, I'll mention that when we do an example. So let's get to the examples. Example 1, I think, is better to do at the very end once you understand this, like once you've done a couple of games. So skip example 1 and join me on the ones that say, like, you find out the ratio. These ones. And I think these are a table. Yes. Okay, so then I have to show all the borders. And give myself room on each one. Okay, and then here's us finding intervals and radii of convergence, at least for the first one. Okay, so you get this power series. It's got x's in it. If it didn't have x's in it, if this was a definite number, I could tell you, does this converge or diverge? Okay, and so that's the idea. Let me see what x's I can plug in that will allow this to converge. Okay, so like I said, you do the ratio test, which is this one. Or you say the limit is n goes to infinity. Technically, it's the absolute value, and that's very helpful in this case because this is alternating series. So, limit of absolute value of, and you plug in, or sorry, you divide the n plus first term over the nth term. So that would be -1 to the n plus 1 plus 1, which is n plus 2. X minus 5 to the n plus 1 over not n but n plus 1 times 2 to the n plus 1 over that nth term. But just to save ourselves a step where we keep change flip, maybe instead of saying over the nth term, I'm just going to say times the flip version of the nth term. Like I'm going to keep change flip just from the very start, just to save. Okay, n to the 2n over -1 to the n plus 1 x minus 5 to the n. Boom. Cool. And then basically, we will run this, simplify this, and we'll talk about what we get once we do. Okay, so this will equal. All right, let's simplify this as much as possible. So Yeah, okay, let's talk about the twos I get first. We got 2 to the n plus 1 and 2 to the n. This just has one more 2 than this one. So all the top 2's will cancel. Most of the bottom 2's will cancel. You'll just be left with a 2 on the bottom. Cool. These negative ones, I was debating not even writing them, but just to be consistent, I wrote them, like just so you see that this is the exact function. But like the negative ones are either making the function negative or positive, and then we're taking the absolute value of this anyway. So I think you're just better off just getting rid of the negative ones altogether. Not that they cancel, but they will not matter after I take absolute values. So let me like clear that on my paper. That's less to think about anyway. Then I got n over n plus 1, which feels like that should simplify in some way, but it doesn't. But let me leave it as n times n plus 1, or sorry, n over n plus 1. And then finally, I have x minus 5 to the n plus first, x minus 5 to the n. So just like the 2's, n of these will cancel n of these, and I'm just left with x minus 5 on the top here.
It's the and stack. On the like the exponents.
Yeah, right. Yeah. Cool. Okay. And then basically we take the limit of this. So if this x wasn't, okay, so I'm sorry there's so many variables. I know this is pretty abstract, but we're taking the limit as n goes to infinity, meaning we're thinking of this x as like I already plugged in an x and it's staying put. So with that in mind, you know what this, okay, good job. Yeah, this limit would be, well, actually, no, it would not be, this part would be 1. It'd be green over 2 more like, because this is kind of the coefficient of the n.
Okay.
Like if this was a 7, green, if this was a green 7, this would be 7 over 2. If this was a green 13, then it'd be 13 over 2, etc. So whatever this green stuff is, the limit would be green over 2, because this is n over n. Okay, so coefficient over coefficient. All right, so finally, we're getting that's the limit. Nice. And then how does this help us? It's because remember the ratio test says run the ratio test. If you get a final limit that's less than 1, then it converges. So we just need to figure out when is this less than 1. Cool. And then now it's an algebra 1 equation. When is this equal to less than 1? So we just solve this, and that's our interval and radius of convergence. Oh god. Okay. So we might run right till the very end, but let's do it. Absolute value of x minus 5 is less than 1. That would mean that either this is, let me make a little number line. Okay, if I want this to be less than 1, then that would mean I want it to be within that range, 0 to 1. But then that means that if it was like negative 0.5, it would also count because the absolute value of that is 0.5, meaning it. So I want this range. In other words, I want this to be between -1 and 1. Okay.
Yeah.
And then now it really truly is just an algebra 1 problem. If you multiply all the sides by 2, so times 2 times 2 times 2, I get -2 less than x minus 5 less than 2. And then add 5 to both sides, and I get 3 less than x less than 7. After you add 5. Okay. And so this is kind of your interval of convergence. But it's like that and not brackets. And the thing is that if I plug in 7 into here, I'd get 7 minus 5 is 2 over 2. So I get this equals exactly 1. And do you guys remember something about the ratio test when this equals 1? Actually, well, okay, you've seen the ratio test one time in your life, but the ratio test when it equals 1 tells you nothing. Like it's inconclusive. It might converge or it might not converge. And so, sorry, but here's me going back to show you this bolded thing. Every time you're asked to find the interval of convergence, you have to check if the endpoints converge or diverge. But now you're in the home stretch. Now you're in the home stretch where you found the hard part. You did all the hard math. Now it's just about checking 2 specific sums. Let me plug in 3 and let me plug in 7 and see which one converges. And I'm sorry, this is so much work, but that's how it goes. So here's me plugging in 3 for x into this series and checking if the result would converge or diverge. And equals 1. -1 to the n plus 1. 3 minus 5 to the n. Oh, God. Should have done the 7 first. In fact, I will do the 7. That'll be easier to explain. Because of the negatives are going to be annoying. Okay, so here's me doing the 7 and the 3. Like I said, I saw this one and I said that's going to be annoying to teach. But let me do the 7 first so they get the idea. All right, watch this. I plugged in a 7. 7 minus 5 is 2. If you don't have room, you can just wait till the end result. But 7 minus 5 is 2. So I now get this sum, and from 1 to infinity, -1 to the n plus 1. 2 to the n over n times 2 to the n. You with me? 7 minus 5 is 2 to the n, 2 to the n.
Oh, yeah.
Okay. And then 2 to the n, 2 to the n, peace out. Now I have this sum. This sum. That sum right there, let me treat it like well, I mean, it is an alternating series. You guys have had a lot of tests, but do you guys remember what the alternating series test does? Okay, alternating series test says that if you got an alternating series that's decreasing in magnitude, as long as this limit is 0, then it'll converge. And that's all 3 of those are true, and I'm running out of room, so I don't want to write all that. But all 3 of those things are true. It's alternating, it's decreasing, and it has a limit of 0. So therefore, this converges. Okay, nice. Meaning when I plugged in 7, I still got that it converged, meaning I include it in my interval.
No way.
I'm sorry. Okay, Gabe. You're good. You got here for the last minute. So I include it in the interval, and then I would have to do the same thing with the 3, but we don't have time for that today, so we'll do it tomorrow. What's up, Kia?
Wait, for the 3s, you kind of see that you're just gonna get -2 to the power of n. Then you can just like, that's literally just multiplying the -1 on top by -1.
But not exactly -1. It's -1 to the n. So this is, well, yeah, this is why I'm gonna get into it tomorrow. So if you have to go, you're good.
But then would it not be an alternate field?
I don't think it is, because
So
this
it
is
would
like,
always be 1, would always be positive or always be negative.
exactly. Yeah, these 2 will end up being even or odd, always negative, I think, and so therefore it diverges. All right, so if you didn't listen, the 3 will not be included, but we'll go into that next time.
And then would it diverge? Because that's like basically 1 over 10, which is like the
Right. Exactly, yeah. Yeah, so this problem's actually done. This will be our final answer, except it asks for the rating. So, okay. Tomorrow we'll go into all of these. This one was the hardest one, but it's the most like you get a number to number interval convergence. The other ones are like, it always converges and it never converges. The other 2 problems.
It was like.